Good morning, students. Welcome to this revision session. In this session, we will look into the module 3, single phase transformer. In this, we are going to understand the necessity of a transformer, principle of operation, types, and construction of a transformer. Then EMF equation, losses, variation of losses with respect to the load, efficiency, condition for maximum efficiency. This particular model is very important and very easy, and you should make sure that you prepare 100% the theory questions, and also the problems are substitution kind of a problem, so you should not miss out. And what is the most important questions from this one is like EMF equation, then losses, then condition for maximum efficiency. So these are the most important questions apart from other questions, and problems based on the EMF equation and problems based on the this condition for maximum efficiency. Those things are very important. What is a transformer? Transformer is a static device which transforms the alternating electric power from one level to other level without changing the frequency. Important thing is the frequency will remain same. Frequency will never get changed. The level of the power will get changed from one level to another level. Suppose if you have the step up transformer, the voltage on the primary side will be stepped up, means on the secondary voltage we will get a higher voltage. In case of a step down voltage, compared to the primary voltage, the secondary voltage will be less. So and transformer is a most essential and important machine in power system, and it has, like, we require transformer everywhere, like starting from the generation until the point of the consumption. Everywhere we have to transform the power level from one level to another level, and that is achieved using the transformer. Normally the transformer generation oh, sorry normally the voltage generation happens at a 11 kV, 33 kV, and 66 kV, and the transmission is done at a very high voltage, 220 kV, or 660 kV, 11,000 kV. Those are the voltages where we do the transmission. There we need the transformer to transform from that generating voltage to the transmission voltage. Again, on the distribution side, we have to step down the voltage until it comes to our domestic usage, where it is 230 volt single phase or 440 volt three phase, that is achieved using the transformer. So we need transformer everywhere in the power system. Now, principle of operation, it works on the same principle, Faraday's same principle of induction, where like whenever the coil or a conductor experiences a change in the flux, EMF is induced in that particular conductor or the coil. So this is the simple diagram of a transformer. This is the core, which is a magnetic material, like a silicon steel, and this core is made up of thin lamination. What square strip you can see is it is like a thick core having a thin lamination, which are put together, stacked together using some kind of a adhesive, which is also a like a insulator, which works as a insulator, keeping all this lamination electrically apart. And on this core, on each of the limb, so on this limb we will have a winding, we call it as a primary winding, and on the other limb we will have similar winding, and we call it as a secondary winding. On the primary side, the N1 is the number of turns, V1 is the applied voltage on the primary, and E1 is the induced primary voltage. Similarly, these are the two terminals where we connect the load. We don't connect the supply here, we connect the load, and the voltage between those two terminals, V2, is the secondary terminal voltage or secondary voltage, and E2 is the secondary induced EMF or the secondary EMF. When we connect the voltage supply here, it will result in the current, primary current I1. When applied voltage is alternating voltage, the resulting current I1 is also an alternating current. When current is flowing through the this particular coil, it creates a magnetic field. Because the current is alternating current, it will produce the magnetic field which is also alternating in nature, and that magnetic flux will flow through this core, which is the magnetic core. This is the magnetic circuit, and during which it will get linked with the secondary coil. Now the secondary coil is experiencing a changing flux. Okay, this changing flux is created by the primary current, so it is experiencing a changing flux. Now the secondary winding is experiencing in the change of flux. Whenever the flux linked with a coil or a conductor changes, an EMF is induced. On the secondary side, EMF of E2 is induced. When we connect the load, the load will start drawing the current I2, that is called as a secondary current. This is the principle of operation of a transformer. Transformer works on a Faraday's electromagnetic induction principle. That is, whenever flux linking with a conductor changes, EMF is induced in it. Okay. Principle of operation: transformer consists of two windings, as I explained you, primary and the secondary winding, having a turns N1 on the primary side, N2 on the secondary side, and wound on a laminated limbs of a core. When AC supply is applied to the primary winding, alternating current I1 will be produced, alternating flux which gets links with the secondary winding. So flux linking with the secondary winding is changing. EMF is induced in the secondary winding, and when we connect a load to the secondary terminals, there will be the load will draw the current, that is the secondary current, represented as I2. And whatever the induced EMF, how we can represent as per the Faraday's law, E1 is equal to N1 d phi by dt. So this is nothing but the Faraday's second law. Faraday's first law tells how EMF is induced. Okay, how EMF is induced: whenever the flux linking with a coil or a conductor changes, EMF is induced. Faraday's second law: how much EMF is induced. So you have to quantify magnitude. How much EMF is induced? That is the second law. The magnitude of the induced EMF is directly proportional to the rate of change of the flux linkage, that is d phi by dt. So E1 is directly proportional to d phi by dt, or E1 is equal to N1 d phi by dt. What is E1? This is the primary EMF induced on the primary winding, because even this winding is also experiencing a change in the flux, so it will induce E1, which will counter the applied voltage V1. And in secondary coil having N2 turns, they are experiencing change in the flux, and E2 EMF is generated, and E2 is equal to N2 into d phi by dt. N2 into d phi by dt. If I take the ratio of E2 by E1, that is secondary EMF divided by the primary EMF, d phi by dt will get cancelled. What remains is N2 by N1. Therefore, E2 by E1 is equal to N2 by N1 is also equal to V2 by V1. So it is not appearing. It is V2 by V1, which is also equal to reverse I1 by I2. So you can see here E2 by E1, N2 by N1, V2 by V1. When it comes to the voltage, it is I1 by I2. When we can say it is equal to V2 by V1, it is like we consider, if we consider the transformer as an ideal transformer, there is no voltage drop between the winding and the terminal between the terminals and the winding. So in ideal transformer there are no losses, so that's why we say E1 is equal to V1 in case of a ideal transformer, E2 is equal to V2 in case of a ideal transformer. So that is how we can write E2 by E1 is equal to N2 by N1 is equal to V2 by V1 is equal to I1 by I2. So you have to remember this relation, which will help in solving the problem. Classification of the transformer. Transformers are classified based on the different categories. One is the number of turns. Depending upon the number of turns, either we can have a step up transformer or step down transformer. Now, how to achieve the step up transformer? Now step up transformer is what? The if this ratio is greater than 1 means E2 by E1 is greater than 1 means that is a step up transformer. If E2 is greater than E1 means, let us say there is 1000 volt on the primary side, 2000 volt on the secondary side, that is a step up transformer. So this would be 2000 divided by 1002, that is ratio is greater than 2. If I want to have a step up transformer, n2 by n1 should also be greater than 1 or n2 should be greater than 1, means the number of turns on the secondary winding should be greater than the number of turns on the primary winding. So wherever the number of turns are more, the voltage is more there. So number of turns are more on the secondary voltage will be more than the primary. If the primary turns are more than the secondary, then the it will be a step down transformer, because primary voltage will be more than the secondary voltage. That is how we can have a either step up transformer or step down transformer based on the number of turns on each of the winding. And depending upon the construction of the transformer, there are two types. We will see the construction: core type transformer and shell type transformer. And depending upon number of phases, so what we are going to see for your syllabus is single phase transformer. We are not going to deal with the three phase transformer, but based on the phases, either we can have single phase transformer, only one phase will be there, or we can have a three phase transformer, there will be a three phases of the transformer. And as we know that transformer is when we use a transformer, certainly there are going to be certain kind of a losses. One of the loss that happens in the winding is called as a copper loss, that is a I square R loss. Means the winding will have some kind of a resistance and current is flowing in that, so there will be definitely I square R loss in terms of a heat. Okay, so it will get converted into heat. Similarly, we have used the core, magnetic core, and even the magnetic core is experiencing in the change in the flux. So we will have loss there also. It is called as a core loss. And again, inside the core loss, we have two types: eddy current loss and the hysteresis loss. All these losses will be in terms of the heat. So heat will get produced depending upon the size of the transformer. We have to have different kinds of a transformer. There are transformers which are very very huge, which will generate lot of heat that has to be transmitted out of the transformer. To keep the transformer safe, we have to use some kind of a cooling mechanism. So based on that, there are different types of a transformer. The first one is the natural air cooled transformer, means we don't have anything additional other than the natural air. Again, it all depends on the different ratings. Okay, as the rating goes higher and higher, we need to have some kind of a cooling mechanism. Then oil cooled transformer. Oil cooled is what? Oil is used for cooling the transformer. Also it will act as a insulator. Then air forced cooled transformer. Air is used, air is blown to take away the heat. That is how the cooling is done. Oil cooled air forced transformer. And certain higher transformer, only one cooling mechanism may not work. So we will have oil cooled as well as the air forced. Again, oil cooled and water circulated transformer. We will have oil cooling. On top of that, there is a circulation on the outer body the of the transformer. Water circulation will be there, which will carry the heat and it will dissipate the heat. And there are other types of transformers also: potential transformer and current transformer. They are used in the instrumentation. Then we have auto transformer. So auto transformer you must have seen in the lab, right? For every experiment, first you take the connection. First you will connect the auto transformer, and from auto transformer you will make the further connections. And similarly, we have distribution transformer, isolation transformer. So there are various types of transformers that are available based on different categories of classification. Next, we will see the construction of the transformer, core type and a shell type. There are two types of transformer. This is a core type. As I explained, we have the magnetic core. It is made with some kind of a magnetic material, like a silicon steel, which has a less hysteresis loss, and thin slices are used. So we don't take a solid core. what we do is we take thin slices of this kind of a strip, okay, square hollow strip, and those thin strips are stacked together. So we will have you can imagine like a book has many pages all together, it forms a book. But here those laminations are stacked together using some kind of a adhesive which will also act like a insulator, and they are bunched together to form the core like this. Okay. And why thin lamination? That is to reduce the eddy current losses. So that will reduce the eddy current loss. Choosing a good material like silicon steel will reduce the hysteresis loss. And on one limb we will be having the winding, the copper winding. These are insulated winding, and on the primary side we will be having the N1 turns, and these terminals are connected to the voltage supply. And on the secondary winding will be on the another limb. Okay. And these windings are also insulated, and these are the two terminals which will be connected to the load. Those are called as secondary terminals, and these are primary terminal. And this winding is called as a primary winding, and this winding is called as a secondary winding. We will have the source, voltage source connected on the primary side, and load is connected on the secondary side. Same description is there. Then we have construction of a shell type transformer. Shell type of transformer, all other things are almost same. We will have a thin lamination for the magnetic core. They are stacked together using adhesive, which is also insulation. We will be having the lamination such that we will get three limbs. So you can see here, this is one limb, this is second limb, and this is third limb. And in this core shell type of transformer, we will have both the windings on the central limb, on the same limb. If you saw like a core type transformer, we had winding primary and the secondary winding on two different limbs of the magnetic core. Here we are having both the windings on the same limb. So this is the primary winding, and this is the secondary winding. Okay. And same number of turns, N1 and N2, everything remains the same. Constructionally, only difference is what we will be having three limbs, and on the central limb we will have the both windings together. Now what happens in this case is, when voltage is source is applied to the primary current will flow through the primary winding, and that will result in a magnetic flux. Now the magnetic flux has a two paths. In case of a core type, we have only one path for the magnetic flux. Here we have two paths. So you can see this is the magnetic circuit. Okay. And rest of the operation, it is exactly the same. There is no difference between the two. So how do we compare the core type and the shell type? In case of a core type, uh, we will have we will have the winding on two separate limbs, and in case of a shell type, we will have the both the windings on the same central limb. In case of a core type, there are two limbs. Here we have three limbs. And in case of a core type, the core surrounds the winding. So you can see, so here you can see, sorry, winding surrounds the core. So we have windings on both the sides, so it will surround the core. In case of a shell type, the core will surround the winding. So you can see the core is surrounding the winding. That is the some of the comparisons between the two. Okay, so these are the here. This is if they ask for the comparison, please first make sure that you draw the diagram. Okay, this is the core type diagram, and this is the shell type diagram. In core type, here both primary and secondary windings are wound on different limbs. It is both on the wound on the same central limb. Only one path for the flow of the flux. So for the flow of the flux, there is only one path. In case of a shell type, there are two different paths are there. Here core is surrounded by the winding, and here the winding is surrounded by the core. Next, most important question, derivation of the EMF equation of a transformer. Now, as I told you, whenever there is a change in the flux, EMF is induced. Okay, that is the principle on which transformer works. But how much EMF is induced? So that equation, even we have to find the equation for the EMF that is induced, so that we can easily quantify how much EMF is produced. This is the representation of the transformer. This is the primary winding. These two lines represent the core. This is the secondary winding. N1 is the number of turns on the primary winding. N2 is the number of turns on the secondary winding. These two are the primary terminals where we connect the voltage supply. V1 is the primary terminal voltage or the primary voltage, and E1 is the induced voltage. Okay, primary induced voltage or the primary EMF. I1 is the primary current, and N2 is the number of turns on the secondary winding. I2 is the secondary current, and E2. So the induced EMF on the secondary side is E2, and these are the terminals of the secondary where we connect the load, and the voltage across these terminals are the secondary terminal voltage or the secondary voltage V2. Now, how much EMF is induced? Again, Faraday's second law, it is directly proportional to the rate of the change of the flux linkage. We know that the when voltage supply is connected to the primary winding, it will result in the primary current, which is sinusoidal. That sinusoidal current will result in a flux, which is also sinusoidal. So the flux can be represented by the equation phi is equal to phi m sin omega t, and according to Faraday's law, how much EMF is generated? It is directly proportional to the rate of change of flux. Therefore, E1 is equal to N1 d phi by dt. Just ignore the sign. Sign shows it is the opposite direction. E1 is equal to N1 d phi by dt. And what is phi? Phi is phi m sin omega t. And if you simplify that one, you get it as E1 is equal to N1 phi m 2 pi f. This cos omega t is just represented as a sine equation, sine omega t minus 90. Now this is of the form, okay, what is this? It is E1. E1 is equal to Em, all together Em. Why Em? N1 for a given transformer, number of turns is constant, and for the primary current, the flux, maximum flux is constant. The frequency of the supply voltage is the constant. So all this is constant. Therefore, E1 is equal to Em sine omega t minus 90 degree. Now, what is this voltage? This is E1 max. We represent it as E1 max. If you want to represent it as a RMS value, I want to know what is the RMS value of the primary induced voltage. We know the relation between the RMS value and the peak value. What is the relation between the RMS value and the peak value? RMS value is equal to 0.707 the peak value. Therefore, the RMS value of the EMF, primary EMF, is E1 max divided by root 2. 1 by root 2 is nothing but 0.707. And E1 max, you substitute with this formula 2 pi f n1 phi m divided by root 2. Now into phi m. So this is the RMS value of the induced EMF. So if you calculate this part, that is 2 pi divided by root 2, you get it as 4.45. That's why the RMS value of the primary induced EMF E1 is equal to 4.44 F N1 phi m. Very, very important equation you have to remember. Okay, where F is the supply frequency, N1 is number of turns on the primary side, and phi m is the maximum or the peak value of the flux. Similarly, if you do the similar analysis on the secondary side, we get the equation E2 is equal to 4.44 F N2 phi m. So you have to see here, the only number of turns is changing here. That's how the induced EMF is directly proportional to the number of turns. If you want to have more EMF, number of turns should be more. And this is the equation you have to remember. E1 is equal to 4.44 F N1 phi m, E2 is equal to 4.44 F N2 phi m, and phi m sometimes they may not give direct value. Instead, they will give as a in terms of a maximum flux density and the area of the core. So that time phi m would be equal to Bm into A. Bm is the maximum flux density and A is the area of cross section of the core. Okay, next, voltage transformation ratio. What is a voltage transformation ratio? Voltage transformation ratio is defined as the ratio of the secondary EMF to the primary EMF, that is E2 by E1. And this voltage transformation ratio is represented as K. K is equal to E2 by E1. E2 is 4.44 F N2 phi m. E1 is 4.44 F N1 phi m. Everything get cancelled except N2 and N1. Therefore, E2 by E1 is equal to N2 by N1. This is what we did in the earlier discussion. Therefore, what we get is E2 by E1 is equal to N2 by N1, or E2 by E1 is equal to N2 by N1 is equal to V2 by V1. So V2 by V1, it has to be ideal transformer. For ideal transformer, E1 is equal to V1, E2 is equal to V2. If they don't specify anything, then it's an ideal transformer. You can assume it as a ideal transformer is equal to reverse I1 by I2 is equal to K, where K is the transformation ratio and it is defined as the ratio of the secondary EMF to the primary EMF. Now, what is the efficiency of the transformer? Efficiency of the transformer is normally very, very high. The reason behind that is transformer doesn't have any moving parts. There are no moving parts, so definitely the efficiency is very, very high. In the exam, if you get any problems based on the efficiency, you should, if there are no issues with the given data, normally you should get a value which is very high, that is greater than 90 degrees. If you are getting a value like 55 or 60, make sure that you recheck your calculation. There might be some mistake, so around 90, close to 90 degree, sorry, 90% you should get. What is the efficiency? Efficiency is defined as the ratio of the output power to the input power. Means how much output I get for the given input. That is the efficiency of any machine. And what is the input power? What happens to the input power? First thing is we get certain thing as a output power and certain thing will go as a loss. Therefore, input power is equal to output power divided plus loss. Efficiency, output power divided by input power. This input power is nothing but output power plus loss into 100. The efficiency can be represented as a percentage or it can be represented as a fractional value. Okay, whenever you multiply with 100, it is a fractional value. And transformers are always represented in a kVA. So what is the power transformer rating? It is represented as kVA. Normally all other machines are represented as watt, but transformer is represented as kilovolt ampere. That is um, um, uh, how we get the kVA on the primary side, V1 into I1. On the secondary side, V2 into I2. Now, let us consider Pi as the iron loss at full load and PCFL is the copper loss at a full load. Now, at full load, the efficiency of the transformer will keep on changing as per the load. At a full load, okay, what would be the efficiency? Eta full load is equal to full load volt amperes. Okay, whatever is the transformer rating, full load VA into power factor. Why we are multiplying it with the power factor? What is output power? Power is always V into I into cos phi, but transformer rating is only VA. So full load VA into power factor divided by output power plus losses. What is output power? Full load VA into power factor plus losses. What are the losses? We have iron loss in transformer, copper loss, plus PI plus PCFL into 100. That is missing. You have to remember, you have to multiply it with 100. This is for the full load. Let us say we have a 100 kVA, and if you are asked to calculate the efficiency with the full load, means that transformer being loaded to 100 kVA, then you will put here 100 kVA and whatever is the given power factor divided by 100 into power factor plus PI, the iron loss plus full load copper loss, you will specify. What if they ask you to calculate the efficiency at 50 kVA? It is a 100 kVA transformer, but the load is just the 50%. Then we use the X value. What is the X? It is the portion of the load or the percent of the load. If I say find the efficiency for 50 kVA, even though the rating is 100 kVA, find the what is the efficiency if the transformer is loaded to 50 kVA. Then you have to use this formula, or this is the most general formula. You can use it for any kind of a load. So you will use it as percentage eta x is equal to x into full load VA into power factor. This whole thing divided by x into full load VA into power factor plus PI. Okay, PI is the iron loss. Iron loss will not change with the load. Okay, whether it is a full load, half load, the minute you switch on, the iron losses are exactly the same. Plus x square PCFL. So you have to remember, you have to put a x square into 100. Now, I gave the example of 50 kVA means what? It is 50% of the 100 kVA. We take the x value as 0.5. Okay, and x is equal to 0.5 means what? It is a 50% load. Or you can see here, 0.5 into full load VA is 100 kVA. 0.5 into 100, 50 kVA. Automatically we get it as 50 kVA here, and this will reduce by the square. X square. 0.5 square is what? 0.25. Means copper loss will drastically reduce. Okay, from full load to half load. If x value is 1, then it is for the full load. X value is 0.5, it is half load. X is equal to 0.25, that is a quarter load. If they ask you to find the efficiency for 10% of the load, x is equal to 0.1, 0.1. Next, condition for maximum efficiency. Now I told you that efficiency will keep on changing with the load. Okay, what is the load? If transformer is rated for 100 kVA, the full load is 100 kVA. What is if transformer is not loaded to 100 kVA, it is loaded to only 50 kVA, then 50 kVA is the load, that is a half load. According to the load on the transformer, its efficiency will keep on changing. There is a one condition where the efficiency is maximum for the given transformer. So this derivation is basically to find at what point the efficiency of a transformer is maximum. Okay, we know output power on the secondary side, V2 I2 into cos phi, that is the power equation. V2 is the secondary terminal voltage, I2 is the secondary current, and cos of phi 2 is the angle between V2 and I2, that is the power, that is the output power. Now, transformer are not to total resistance of the transformer referred from the secondary. Now, every transformer has a resistance. Why? Because we are using the copper winding. Even though the resistance is very, very less, we have the resistance of the primary winding and the resistance of the secondary winding. Either we can take it as a separate, or we can refer it from the secondary side and we can find the total resistance of the transformer. So R02 is the resistance of the transformer with respect to the secondary side. Because we are dealing with the output, we are taking the resistance with respect to the secondary winding. If R02 is the total resistance of the transformer with respect to the secondary winding, total copper loss would be I2 square R02. Okay, what is I2? I2 is the secondary current. Okay, I square R is the copper loss. Okay, I2 square into R02. And what would be the total loss? Pi plus Pc. What is Pi? Pi is the iron loss plus Pc is the copper loss. Then we can write the equation for the efficiency: output power divided by the output power plus losses. V2 I2 cos phi 2, V2 divided by V2 I2 cos phi 2 plus Pi plus Pc. And we know what is Pc. Pc is nothing but I2 square R02. Just we will replace that. We will replace here. Then we'll take the I2 common. Okay. On the numerator, I get V2 cos phi 2 divided by in the denominator V2 cos phi 2 Pi by I2 plus I2 into R02. Then I2 will get cancelled. Now, what we want is the maximum efficiency. How we can achieve the maximum efficiency? By having a very large value for the very small value for the denominator, then we can have a maximum efficiency. Okay, if denominator value is much less than the numerator value, what we will get is a maximum value for this ratio. But V2 is constant for the given voltage, phi 2 is constant, we cannot change the numerator, and here also V2 cos phi 2, this is constant. Pi, iron loss for a given transformer is constant. R naught 2, resistance of a particular transformer, is also constant. What is the variable here? I2 is the only variable, and numerator we cannot make any changes. If we can make value of the I2 such that this value goes down, and we get the higher value for the ratio, then we will have the maximum efficiency. For maximum efficiency, denominator differentiate with respect to I2 and equate to 0. So that is how we can find by having d by I2 of denominator equal to 0, which will give me a minimal value for the denominator. Okay, so if you perform this particular differentiation with respect to I2, we get it as like V2 cos phi 2, this will become 0, Pi into 1 by I2, so 1 by I2 minus 1 by I2 square, plus d by I2 of I2 is 1 R naught 2. So what will remain is minus Pi by I2 square is equal to minus R naught 2, or minus Pi is equal to minus I2 square R naught 2, or Pi is equal to I2 square R naught 2. What is I2 square R naught? It is nothing but the copper loss. Therefore, Pi is equal to Pc. So this is the condition when copper loss is equal to iron loss. When we see, as the load changes, the copper loss will change. At certain point, the iron loss will become equal to the copper loss. That is when we have the a maximum efficiency. When iron loss is equal to copper loss, the transformer efficiency will be maximum. Now, this is in terms of a portion of the load. What they will ask in the exam is, they will first ask what is the portion of the load when we have the maximum efficiency, and also they will ask you at what load, at what load in terms of a VA. Then we can multiply that portion with the full load VA. First of all, first condition is what? Iron loss is equal to copper loss. That is Pi is equal to PC. But this PC can be, what is PC? PC is I2 square into R naught 2. That I2 can be represented as a full load copper loss, and X into full load copper loss. So X into full load current. Okay, portion of full load current. So for example, for 100 kVA, the full load secondary current is, let us say, 100 amperes. I can represent a certain load, okay, as X amount of full load current. So that is how I get this PC copper loss can be represented as a portion of full load copper loss. So X max square into PCFL, or X max is equal to square root of PI by PCFL. Means how I can find at what portion of the load the maximum efficiency occurs. X is equal to square root of Pi by PCFL, or square root of iron loss divided by full load copper loss. This is a very important relation you have to remember. X max means at what portion of the load we get the maximum efficiency. If you know the iron loss and full load copper loss, square root of iron loss divided by full load copper loss. Now, what is the output VA or the KVA for maximum efficiency? Whatever the portion you get, multiply with the full load VA. So that will be very useful for the your problems. Now you can say transformer losses. There are two types of losses in the transformer. One is called as a core loss or the iron loss. Second one is the copper loss. The core loss or the iron loss are further divided into hysteresis loss and the eddy current loss. And hysteresis loss is given by KHF Bm raised to 1.6. So KH is a constant, F is the supply frequency, Bm is the maximum flux density. Okay, and if you see here, kh is constant, f is constant, and bm is constant. So this value is constant. Eddy current loss, ke into f square into bm square into t square. Ke is constant, f is supply frequency, bm is flux density, maximum flux density, t is the thickness of the lamination. So now you know why we are taking the thin slices. If we reduce the size of the slice, if t is reduced, the eddy current will reduce. And for a given transformer, the thickness would be constant, right? So that is how this is constant, hysteresis loss is constant, eddy current loss is constant. And the core or iron losses is the sum of hysteresis loss and current loss. That is why it is constant. Core loss or iron loss for a given transformer will not change, it will remain constant. However, the copper loss, which is a I square R loss, which will change. How do we represent the copper loss? Copper loss is equal to I square R loss on the primary side plus I square loss on the secondary side. R1 is the resistance of the primary winding, R2 is the resistance of the secondary winding. So what is the loss on the primary side? I1 square into R1 plus loss on the secondary winding is I2 current, I2 is the secondary current, I2 square into R2. Or if we get the total resistance with respect to the primary winding, that is R01, then we can have copper loss as I1 square into R01. From secondary side, I2 square into R02, where R02 is the equivalent resistance with respect to the secondary winding. Now you can see from this equation, I2 square into R02. R02 is constant. The resistance will be of the transformer is constant. The copper loss will increase as the square of the load current. Means if current is flowing 5 amperes, then if it is increased to 10 amperes at 5 amperes, we will assume this as 1 ohm. So it is 5 square is 25 into 1, 25 watt loss will be happen. If current doubles to 10, so it will become 10 square, that is 100 into 100 watt. So from half load to full load, it will change to from 25 watt to 100 watt. So as you keep on loading the transformer, the secondary current will increase and the copper loss will increase. Suppose you don't connect any load, the copper loss is zero because no current is flowing in the secondary. But the copper loss is same whether it is no load or full load, half load, any load. The iron or the core loss will remain constant. Copper loss will change according to the load. Next, voltage regulation. What is a voltage regulation? Voltage regulation is when we normally we have a transformer which has a a step up or a step down voltage. A secondary voltage is given, okay, with a rating. But that particular voltage, when we keep on loading the transformer, it will start dipping. Okay, so that is called as a voltage regulation. Normally the transformers will have about 2 to about 3 to 5% voltage regulation. So percentage regulation is defined as voltage regulation of a transformer is defined as the ratio of the difference in no load voltage to full load voltage to no load voltage, and is expressed in percentage. What is V naught? V naught is a no load voltage, means voltage on the secondary terminal when there is a no load. Let us say 250 is the secondary voltage, that is on no load. When you load the transformer, that 250 will become 240. So this is 240 minus 240 divided by 250. That is called as the voltage regulation. So there are problems based on the EMF equation and problems based on the efficiency. That some of the problems we can see in today's class. So based on the whatever the equations you have learned, we will be having the problems. So it is very simple substitution kind of a problem. So we have 25 kVA transformer has 500 turns on the primary, that is N1, 40 turns on the secondary N2. The primary is connected to 3000 volt. This is E1 or V1. F is given. You have to find primary and secondary currents on full load. So full load is what? 25 kVA. Okay. And what is 25 kVA is equal to on the primary side V1 into I1. What is secondary side? Full load voltage V2 into I2. That is equal to 25 kVA. First, you can find the transformation ratio. N2 is given, N1 is given, 40 by 500, that is 4 by 50. Then uh, so for finding a primary and secondary full load current, on the primary side, V1 into I1 is equal to this full load 25 kVA. Therefore, I1 is equal to volt amperes VA divided by V1. That is, VA is what? 25,000 VA. 25,000 divided by 3,000, we get it as 8.33 amperes. Therefore, I2 is what? I1 by K, 8.33 into 50 by 4, we get it as 104.2 amperes. So, when transformer is loaded to 25 kVA, 8.33 amperes is the amount of current flows on the primary side. 104.2 amperes current flows on the secondary side. Now E2 by E1 is equal to K. We have to find the secondary EMF, right? E2 is equal to K into E1, that is 4 by 50 into 3000, we get it as 240. You can see here 240 voltage, number of turns are less on the secondary, we get less voltage. On the primary side, we have 500 turns, we get 3000 volt. Now the maximum core flux. So in order to find the maximum core flux, where is the flux, which equation has the flux? E1. E1 is equal to 4.44 F N1 phi m. E1 is known, F is known, N1 is known. So you can calculate phi m. The phi m will come as 27 into 10 raised to minus 3 Weber, 27 milliweber. So similar, very simple substitution kind of a problems are there. Now in this particular problem, they have asked what is N2, so that you can easily find out. So this here they are asking the RMS value of the secondary EMF. They have given the flux, number of turns, and frequency. So straightforward substitution, you get the answer. In this example, they have not directly given the flux, they have given the area and they have given the BM. Okay, and for finding area also, you have to find you have to consider for the flux. To allow for the insulation of the stampings, assume the net length is 0.9 the gross length. So the gross length is 20 centimeter. So one side is 20 centimeter, one side is 20 centimeter, and another side is 0.9 20 centimeter, because we have to take away the laminations, whatever insulation we have used, that we have to take. So effectively it is 18 centimeter. What would be the area? 18 into 20, this is the area. And make sure all the units are in meter. Okay, all are in the base units. So that kind of a problems you can expect in the exam. Okay, based on the efficiency, you can see here we have a transformer 50 kVA. This is full load VA. Iron loss is 500, so this is PI 500 watt. Full load copper loss, this is PCFL. You have to identify correctly, then it becomes very simple. 800 watt. Find the efficiency at full load and half a full load at 0.8 power factor. Power factor is given as 0.8. I recommend you to use the formulas that we have, the generic formula that we have created, that will become simple. If you remember in the class, we have solved like that, not like the one that is given in the book. So we use this formula. Okay, eta x is equal to x into full load VA into power factor divided by x into full load VA power factor into power factor plus PI plus x square PCFL into 100. Okay, so if I use this formula, what is first is I have to find full load efficiency, and power factor is 0.8. So here full load means what? X is 1. 1 into, it is how much, 50 kVA transformer, 1 into 50 into 10 raised to 3, power factor is 0.8, divided by 1 into 50 into 10 raised to 3 into 0.8 plus PI, they have given it as 500, and PCFL is 800. 500 plus 1 square into 800, whole thing multiplied by 100. You will directly get the efficiency. Or you can use this method. Whichever is easy for you, you can do that. Similarly, for the half full load. In case of a half full load, everything remains the same, no change. Only X, instead of 1, you take it as 0.5. Here it would be 0.5, here it is 0.5, 0.5 square. So you will get the efficiency as 96.6. Okay, so this is the load for maximum efficiency condition is given. Okay, 40 kVA transformer, iron loss PI is 450, full load copper loss PCFL 850 watt. If the power factor of the load is 0.8, PF is given as 0.8. Full load efficiency, same formula we can use what we discussed earlier. kVA load at which maximum efficiency occurs. Okay, so when the maximum efficiency occurs, when PI is equal to PC is equal to 450, correct? That time maximum efficiency occurs. And how to find at what load? Okay, what kVA load? So you have to remember this formula. Remember, we derived that formula. Okay, this formula. So this is the portion of the load at which maximum efficiency occurs, square root of iron loss divided by full load copper loss. So that's why you have this X, they are multiplying it. This will give me the portion multiplied by full load VA. Okay, this is multiplied 40 into 10 raised to 3. So square root of iron loss is 450 divided by 850. That you get it as 40 into at 29.1 kVA. Means if you load the transformer to 29.1 kVA, it will give the maximum efficiency. And what would be the corresponding output in terms of kilowatt? VA into power factor, 29.1 into 0.8 at 23.3 kilowatt, it will give the maximum efficiency. And what is the last thing that is asked? What is the maximum efficiency? Now we know at what load we are getting the maximum efficiency. So if you take X max as this, so square root of 450 divided by 850, you will get some X value. You use that X value in this formula. Okay, whatever the general formula we have, use that X value here, here, and here. Rest are same. You will get the maximum efficiency, or you follow this method. So those are the different kinds of problems we you can expect in the exam. Okay, this is another kind of a problem. Here they will give two conditions, and you have to find what is PI and what is copper loss, full load copper loss PCFL. Efficiency of a 400 kVA, this is full load VA. Single phase transformer is 98.77 when delivering full load. So X is equal to 1 at 0.8 power factor lagging. And this is half load efficiency 99.13, half load X is equal to 0.5. Unity factor, power factor is 1. Calculate iron loss and full load copper loss. So they have given two efficiencies, means two efficiency conditions, and we have two unknowns, PI and PCFL. So you can get two equations, right? One is X is equal to 1 and another is X is equal to 0.5. They have given, this side is not unknown, they have given the efficiency. You will get the equation in terms of first equation as PI plus PCFL is equal to something. Second equation where the load is half, 0.5 square is 0.25. So you will get PI plus 0.25 PCFL is equal to something. So you have two equations and two unknowns. You can easily solve. Okay, so first equation you get it as Pi plus Pc is equal to 4000, and second equation Pi plus 0.25 Pc is equal to 1800. And if you solve these two equations, you get the iron loss as this much, 1.07 kilowatt, and copper loss as 2.93 kilowatt. So there will be similar kind of problems, easy problems that you can solve. I will attach this also with to this video, and you will be able to go through. But better, instead of, you can, if it is easy for you, you go this method, or better method is always use this formula. So just check what x value should be substituted, and what power factor, and rest of the calculations are as per the given condition.